Hello and welcome back. Okay, in example 1, we've got our first challenge. Here, we're asked to use the given graph of f to find a number delta such that if x is within delta of 2, okay, there I see 2 in the graph, there's the x value of 2. So within delta of 2 is going to be some delta interval about 2. So if that's the case, then f of x is within 0.25 of 0.5. So there's the limit L right there of 0.5. This is L. And we want to be within 0.25 of that limit L. So there's our epsilon challenge. Epsilon is 0.25. That's how close we want to get to L. Okay, so this is like L plus epsilon, and this is like L minus epsilon. Notice that the distance from here to here is 0.25, and between 0.5 and 0.25 is again a 0.25. There's your epsilon. In fact, I think I'm going to write these like this: from here to here and from here to here. Okay. So we're going to have to find a delta that's going to respond to this epsilon challenge. We want to make it so that when x is within delta of 2, that when we plug in all those x values into the function, all the x values on that interval, about 2, if we plug them all into the function, that the y values are going to be within 0.25 of 0.5, so within epsilon of this limit L. Well, it looks like if we're thinking about x values going off to the left here, we've got, let's see, we've got a distance between 2 and 1.3. That distance, let's write it out. That distance there is 0.7. And as long as we don't stray farther than 0.7 to the left, all of those x values are going to fall within that epsilon tube, right? It's only when you get to 1.3 that you're right at the boundary. When you plug that in, you're right on the boundary of that epsilon interval, or that epsilon tube. So if you stray too far beyond 1.3 to the left, you're going to fall outside of that epsilon tube. You're going to be too far from that limit L. So on the left side, our boundary is 1.3. On the right side, if we go from 2 to the right, then we head out to, if we, looks like we get to 4. 4 is going to be the farthest out that we can go if we're moving our x values to the right, if we're thinking about moving our x values going to the right. If you go a little bit farther than 4, you're going to stray too far away, and your y values are going to be too far from 0.5. They're not going to be within epsilon. They're not going to be within 0.25 of 0.5. So the safe zone is right here. It's 0.7 to the left, and it looks like 2 to the right. But with delta, we only get one number to choose, one closeness to 2. That's going to make an interval, and all of the x values on that interval, when we plug them in, are going to have to be within 0.25 of 0.5. So what would that number have to be? What would the closeness to 2 have to be? If you said 0.7, then that would be correct. Now you could have chosen actually something smaller, like 0.5, that would also work, or 0.01. But here, usually what we're going to be looking for is the largest possible delta that could possibly still work. Otherwise, everybody would just write delta equals 1 times 10 to the negative Google, and then I guess that would probably be correct. So we're gonna write the largest delta, but just a side note that technically speaking, any smaller number, as long as it's positive, would work too. But this one's good. This one is good because if we consider our delta interval with 0.7, so that would be 1.3, and then over here it'd be like 2.7. If you consider all of those x values, if if you consider all those x values in that delta interval, plug them into the function, all those y values will be within 0.25 of 0.5. That satisfies this condition. All those function values, all those y values are going to be within 0.25 of 0.5. Okay, so we responded to that epsilon challenge. Great. I think I'll end the video here, and we'll go on to example 2 in the next video. Thanks for watching, and see you in the next video.